Hello YouTube! Today we're going to be talking about how to find the net force on an object. There are actually a couple ways to do this. In particular, today we're going to be saying if you know what all the forces are, how can you find the net force from there? Um, so let's hop to it. Ideally, end of the day, you should be able to use Newton's first to predict the motion of an object. And remember how the Newton's first law is that net force causes accelerations. We need to know whether or not there's net force. So the big thing for today is finding the net force on the object and figuring out whether or not it's zero, which you can then use to say, okay, well, whatever direction the net force does go in, if it's not zero, that'll be the direction it's accelerating. So, net force is the sum total of all forces on the object in each direction, including their directionality. Way more complicated than it needs to be. If you've heard of the phrase net worth, what that's referring to is how much money someone has, but it includes any debt that they have. So what you do is you take anything they have that's valuable, and that's positive. You take anything they have that's debt, and that's negative. And when you combine those two things, it gives you the total amount of their worth. Very similar with forces. When we talk about net force, what we're describing is not just adding up the numbers from all the forces, it's being really careful about which are positive and which are negative. The way that gets written is with the symbol sigma. This is a Greek letter. This whole thing altogether is one variable. It means the net force. Sigma is something that in math means the sum of all. So the sum of all, meaning adding up all the forces, is one concept of net force. So you can break this up, and for this class we're going to be doing a lot of this, into the net force in the x direction and the net force in the y direction using trig. The reason why we do this is because if you think about how vectors work, hopefully you've seen that part of Unit 0. If you haven't, links in the description. Stop now and go watch it. This is sort of the big reason we went into that, is that our vectors don't add unless we've broken them up into components, and then the parallel components from the vectors will add. And then we can represent it as two perpendicular components to get our final vector. So in order to find the net force, that's basically just what you do. You do vector addition on every single vector that's in the problem. So few examples of that. We've got one block. This is unit 2.2 at force. So we've got two blocks, one of which is experiencing a force of 8 newtons going up, 10 newtons going down, 5 newtons to the right, 5 is not an F, and 1 newton to the left, and 2 newtons to the left. In theory, I should be trying to keep these sizes relatively consistent, so the 8 should be bigger than the 5 and smaller than the 10. So this is our first problem. Our second problem is going to be a wee bit more complicated, and by a wee bit more complicated, I mean a lot more complicated, because it'll actually involve trig. So we've got one force that's going up and to the left of 8 newtons, one force that's on it that's going up, that's 3 newtons, one force on it that's going down, that's 5 newtons, and then we have a 10 newton force going up and to the right. That 10 newton force is at a 37-degree angle, that 8 newton force is at a 60-degree angle, and that's our problem. Oh, and this is a 10 newton force. I should label that. Great. Now that we've got everything labeled, let's do it. So, first off, in particular for these, a lot of times what you're going to be doing is breaking things down into an x direction and a y direction. So in the x direction, if we want to find our net force in the x direction, the way we write that is net, or sum, of our forces, and then a subscript telling us that it's the x one. In this case, that'll be equal to our 5 to the right. I'm just going to take that, represent it as plus, because it's to the right. Anything going to the left, I'm going to make minus. So minus 1, minus 2. And then I just have to add all those up. 5 minus 1 is 4, minus 2 is 2. So positive 2 newtons to the right is our force in the x direction. In the y direction, we've got 8 going up, so plus 8. we've got 10 going down, minus 10. So that'll give us minus 2 newtons. If you want to write that, we could say that the net force is equal to plus 2 comma newtons. I should be careful about that. Minus 2 newtons. And that would be a way to write it with our vector components. So we've got it all in one thing. If you really want to go overboard, you could take this and do the angle and magnitude notation. But like for now, let's just keep it simple. All right, number 2 is going to be a little more intense. So the big thing here is that we're going to have to break stuff up into components. So we'll have an x component for each of these, and we'll have a y component for each of these. And coming over here, we'll have an x component, and we'll have a y component. Our x component for this 8 Newton force is next to our 60-degree angle. It's touching it. So that one's going to use cosine. So 8 times the cosine of 60 degrees will give us our x component for that one. This one over here is opposite. So that one's going to be the 8 times the sine of 60 degrees. Again, I'm sort of skipping some steps here and going pretty quick on the trig. Watch the trig video if you're struggling. Over here, our y component is the one that's adjacent, so our y component is going to use the cosine. And our x component is opposite to the angle, so our x component is going to use the sine. Taking those and throwing them into a calculator, we've got 8 times the cosine of 60, which is 4. We've got 8 times the sine of 60, which is 6.9. And we've got 10 times the cosine of 37, which gives us 4.98, which I'm going to round to 8. And lastly, we've got 10 times the sine of 37, which is 6.01, and I'm going to round that to 6. Should probably have equal signs after this. Great. So if I want to find my net force, now that I have the components, nice and easy, it's the exact same thing as problem 1. The only thing you want to be careful for, the whole point of breaking up the component diagonal into their components is that you don't have to worry about is so that you can use them and that those components represent the same thing as the diagonal. So don't try to also include the diagonal. Once you've got the components, that's the only thing you're using. So in the x direction, we'll have our 6 from, which is still our net force in the x direction. We'll have our plus 6 going to the right. We'll have our, from our 10 Newton vector, we'll have a minus 4 going to the left from our 8 Newton vector, and that'll give us plus 2 newtons as our net force in the x direction. For our y direction, our net force in our y direction will equal the plus 3 from this standalone vector that's just going up. We didn't need to break that one into components because it was already in components. It's just up and nothing in the x. Our minus 5 from our vector going down, and our plus 6.9 from our 8 Newton vector going up. 3 minus 5 is negative 2. 6 minus 2 is 4. So 4.9 newtons going up. And there's our net force. So really quickly going over the process for this again. Your first step is going to be making sure that you have everything drawn. Your second step for all of this, I'm going to get this in a color, slightly different color, will be to use trig to get components. Your third step is going to be add them up in x and y. And you do one separate equation, one for x, one for y. There's going to be a second thing that net force is equal to a little bit later on. And so in particular, I want you to stay open to the idea that this is literally just a way to find net force is to add everything up. If there was a second way, those two things would be equal to each other. And that's sort of the crux of the entire unit. But really focus on this part of it and make sure that this part makes sense and you're good to go with it. A lot of times what will happen is the trig gets pretty overwhelming. People get too caught up on the trig, and then this gets needlessly hard, and you're not really thinking about what's happening while you're doing it because you're so focused on the trig. So really make sure that you're good at the, good on this, good at finding the components, good at knowing what they mean, and good at knowing like what all of the mechanics behind all this stuff is, because a lot like our basic vocab from last unit, these are sort of the ABCs of this unit, and if you don't know the alphabet, it's a lot harder to learn how to read. So this is sort of the alphabet part. Really make sure you're good on this. All right, great. So thanks, and goodbye, YouTube.